In today's tutorial on medicinal drugs, we will have a look at thalidomide. It is better known under the name Contergan and is infamous for being highly teratogenic. Initially, it was meant as a substitute for other sedativa and sleeping pills such as carbomel and cycloparbitol. These are itself problematic because here we have a problematic bromide, some kind of alkylating agent, and even the bromide and ions can cause severe problems. Cycloparbitol, for instance, is known to be deadly in an overdose. So, these problems are not associated with thalidomide, but the horrible teratogenicity. So, as sleeping pill, it is off the market, but it is still in use against leprosy. So, we have two enantiomers, and normally one should bring a drug on the market if one has only if it's enantiomerically pure. But in this case it doesn't matter, because thalidomide can easily undergo a racemization under slightly acidic conditions, and if you swallow a pill while you have slightly or even higher acidic conditions in your stomach, of course. Now, what we want to clarify is, why does thalidomide easily undergo a racemization while amino acids are notorious that they racemize very slowly? Well, I've chosen glutamic acid here because this is the amino acid that is underlying this structure of thalidomide. So, we have the nitrogen here, we have the 4-carbon chain with 2 carbonyl groups, exactly as in glutamic acid. And indeed, the synthesis of thalidomide starts from glutamic acid. So, glutamic acid only slowly racemizes under moderate conditions. You can use amino acids to determine the age of samples, well, between 1,000 and 100,000 years, just determining what is the percentage remaining of the naturally occurring L enantiomer of an amino acid compared to the D enantiomer. It takes, under temperatures of about 20 degrees, about 100,000 years that it completely racemizes. So, thalidomide is much faster. Well, for the racemization, you need to protonate at one of those carbonyl groups here, to protonate, then to deprotonate, to get to this intermediate with an enol structure. It is important for the stability of this enol structure that we have a phthalimide, a phthaloyl protecting group at this nitrogen, because the electron pair of that nitrogen is conjugated to the carbonyl groups. They diminish the electron density here compared to, well, the amino acid without that protecting group. Then this free electron pair would donate even more to the olefin, and too much of electron density is not stable. In addition, this enol has the opportunity to form a hydrogen bridging bond between the OH group and that carbonyl group, further stabilizing this structure and also being responsible for diminishing the energy barrier to this intermediate. Nevertheless, these non-conjugated structures of thalidomide are the more stable ones, and therefore that equilibrium arrow is longer in the direction of these thalidomide structures. Thanks for listening.